welcome to Paris and to the International School of Astrophysics, Daniel Chalonge, Ecole for this closing lecture of the year. And it's a great pleasure and a great honor to welcome here today again Professor Dr. Adam RIESS, Nobel laureate in physics, Chalonge Medal and Ecole-deVega Medal, a new H0 award, and for the expansion history of the universe. Adam was born, I will briefly present him because I see in the audience many newcomers here. And Adam was born in Washington, D.C., grew up in New Jersey, did the graduation in '92 there at Massachusetts Institute of Technology, and PhD in Harvard in '96. And in '99, surprising, I mean, his career is really a great successful a series of surprising results for the universe. And in 1999, obtained a surprising result, and with a new type of supernova of great importance in astronomy. His PhD thesis was in fact very highlighted and obtained a very important prize. And then after was in California at Berkeley, and in '99 moved to the Space Telescope Science Institute. In 2002, got the position in Johns Hopkins University's Bloomberg Distinguished Professor. Is also Thomas Barber Professor of Physics and Astronomy, and led together with Brian Schmidt, the High Theta supernova team, which discovered the acceleration of the present stage of the universe, and for which he got the Nobel Prize in physics. Got also the Einstein Medal and several other awards. More recently is, again, in fact, he was always at the center of cosmology from the very early universe to the late universe in which we are. And it's for this reason, and the previous one, that he got from this school the two medals, the Chalonge and the Ecole-deVega medal, and a new award on the, which we call H0 award. And he have inspirations from this school, and in fact is Adam who has inspired to us this award. And we are greatly pleased to have Adam with us today. And so, Adam, the floor is yours, please.
Okay, can you hear me okay? Okay, you're muted now, but I guess that's okay. Norma, can you give me a thumbs up if you hear me?
Fine.
Okay, excellent. Good. Well, it's a pleasure to be back here. I spoke here last year, and to be honest, Norma sends me a good bottle of French champagne every year, which I think is the bribe to come back and speak again, and it works. So I'm happy to be here. I'm going to tell you first in a colloquium style, a little bit of background, the surprises that the expansion history of the universe has been throwing at us. And I'm going to highlight a couple of new results this year, listed there at the bottom, 2 new papers from my collaborators and I, based on a new calibration of the distance ladder using cluster Cepheids from Gaia, and also a first look at Cepheids in supernova hosts and the distance ladder with JWST. Okay, but let me start at the beginning. You always have to start at the beginning. One of the only ways that we can learn about the composition, the age, and the fate of our universe is by watching it expand around us. Given that the universe looks homogeneous and isotropic on large scales, and assuming that general relativity holds across the universe, we can derive the equation of motion for the universe, how the scale factor, A, the size of the grid that you see on the left, how that will change as a function of time due to the physics of the universe. And that is encapsulated in the famous Friedmann equation, almost 100 years old now. And so on the left-hand side is the differential or kinematic behavior of the expansion of the universe, which observers can measure. And on the right-hand side is all the interesting parts of the universe that we want to learn about. Now, we don't directly observe A as a function of time, but we observe proxies. We observe redshift instead of A, but those are closely related. And we measure distances instead of look back time, but those are related by the speed of light. And if we have bright enough, long range enough tools, we can actually look into the past by looking out and measure how this function has changed with time. Now, of course, a couple decades ago now, it used to be that the universe was thought to be so simple that it would be matter dominated, that most of what you needed to learn about the function A of t was just the first 2 derivatives. So A dot, of course, is what we call the Hubble constant, the present expansion rate of the universe. This was once debated to a factor of 2. Now it's debated to a much smaller factor. That is progress. And I will speak more about that later on in the talk. And the second derivative of A, the deceleration parameter, defined to be decelerating because in a matter-dominated universe, the universe will decelerate, but that turned out to not be the case. This is something we learned about in the 1990s by the use of really long-range standard candles. So I'm going to discuss 2 kinds of standard candles. Just a reminder, a standard candle is any object whose luminosity you understand or can standardize so that by measuring its brightness, you can determine its distance. And so I'm going to use 2 that are sort of the gold standards of standard candles. Type 1a supernovae, which are exploding white dwarf stars, which approach the Chandrasekhar limit and reach billions of solar luminosities when they cross the Chandrasekhar limit, probably because they live in binary systems with some kind of mass transfer mechanism. The details of that are still unclear. And Cepheids. These are pulsating supergiant stars. They're less luminous than type 1a supernovae, but they are far more common. So they have a particular value, which I'll talk about. They have a tight correspondence between their period and their luminosity, which really is just a scaling relation, that the period scales the mass and scales the luminosity. That's well understood from theory, but at the end of the day, we calibrate them empirically, and I will talk more about that a little later in the talk. Now, as I said, in practice, these are not always standard candles, but we can standardize them. And further, we measure their colors and compare them to what we would say is unreddened or unobscured versions of them, because sometimes there's dust in galaxies which can redden the light. And if we can measure the amount of reddening, we can relate that to the amount of dimming to return these objects to being good standard candles. Okay, so I think people are probably widely familiar, but nevertheless, it was by the early 2000s that I would say the first draft of these parameters had been measured. The Hubble constant measured from the Hubble Space Telescope Key project, observing Cepheid variables in nearby galaxies, had measured to 10%. The Hubble constant to be about 72, and the deceleration parameter turned out to be the acceleration parameter. That was our first big surprise. And of course, that raised really what is, I think, the big, if not the biggest, one of the biggest questions in cosmology is, why exactly is the universe accelerating? What causes that? And we can understand that, at least mathematically, in general relativity as something that we call dark energy, which really means some kind of fluid or energy in space that has a negative equation of state. In fact, less than minus a third, the ratio of its pressure to its energy density will, in general relativity, cause repulsive type gravity. What is the source of this energy? We're really not sure. Our first best guess is that it is vacuum energy, a constant amount of energy, what Einstein would call the cosmological constant, and what we call lambda, or lambda CDM, when you combine it with the rest of our understanding. This is not a crazy idea. It's sort of expected in quantum theory. And in general relativity, it will give rise to repulsive gravity. But of course, everybody knows there's a terrible quantitative mismatch between the idea that comes from quantum theory and what we actually see. And so that's why we really can't take this as anything more than phenomenological. Option two would be dynamical dark energy. This would be the energy in space due to a scalar field that might be temporary, and the potential energy of that field would act just like a cosmological constant, although it might be changing over time and space. We might hope to see that. Both these ideas have existence proofs. The Higgs field, for instance, is a static energy in space, and inflation, assuming that occurred, would be a dynamical dark energy. And then option three is if general relativity breaks down on long range distances. And all of these ideas can be tested with very precise measurements of the expansion history of the universe. Now, one of the most powerful ways to, I'll say, move forward in this field, given the lack of certainty, particularly on option 2 and 3, that don't even have a specific form they have to take, is to just assume option 1, because it's the easiest thing to calculate. You can define the consequences of most any experiment given the assumption of option 1, and then we can look for departures from that. And so what I'm going to talk about for the rest of this talk is the sort of grand end-to-end test of the universe, or of lambda CDM, which can be undertaken by predicting and then measuring the value of the Hubble constant. So given lambda CDM as an assumption with its 6 free parameters, and assuming the most vanilla forms for the parts that we don't really understand. So in the case of dark matter, we assume it's a particle that doesn't have collisions, is perfectly static, it's perfectly stable and cold. It has no other interactions except for gravity. We don't know these things are true, but these are assumptions we can make to make predictions. And then dark energy, we assume that it's a cosmological constant. And so we can then use this model, and the model doesn't look the same today. It would have in the past at redshift 1,000 or higher. The model looks very different. Atoms, photons, and neutrinos become very important. But we can use the model in that form to predict the scale of fluctuations in the early plasma of the universe, the physical scale, and we can compare that spectrum of fluctuations to the angular fluctuation spectrum that is observed in the cosmic microwave background. And in that step, one can compare the model to the predictions and learn the free parameters of the model. So if you look over on the right, there is an example of the power spectrum. I think that one's from Planck. And what I'm showing you there in the lower right is how you can vary the 6 parameters and change the form of the power spectrum. And so you go through that process to finalize your estimates of those free parameters. Now, once you've done that, you can then predict the expansion history of the universe, the blue curves that you see right there. And through that process, we can predict that the value of the Hubble constant today should be 67.4 plus or minus 0.5, assuming that we have the right cosmological model, we have the right physics of the universe that includes both as the universe looked before recombination, which includes things like the number of neutrinos or any interactions of neutrinos. It includes the properties of dark matter at early times as well as at late times. But if we have all that right, or it takes the simplest form, then we should be able to measure this value of the Hubble constant. The alternative approach, the direct approach, which I'm going to talk more about in this talk, is to make measurements locally of the Hubble constant and see how those agree. This is interesting both for understanding the physics of the universe. It's also interesting from the standpoint of the age of the universe, because the age implied by these different possible expansion histories does involve different possible ages for the universe. Okay, so we anticipated more than 15 years ago now that the cosmic microwave background data would become so good that this would become a really powerful complement to make a direct local measurement. And we thought we could get to percent level precision using the Hubble Space Telescope by leveraging the two sort of gold standard tools for long range distance measurements, Cepheids and supernovae, and calibrating them geometrically with new tools available for that. And I'm going to say more about that in a minute. We saw various ways to cut down on systematic errors along the distance ladder. I think the key element in there is making all measurements differential as much as possible and making those measurements in the near infrared to reduce the effects of dust. Also thorough propagation of statistical systematic errors, and particularly covariance, which I'm going to talk about later in this talk, is a new element just in this last iteration. This was not the Hubble Space Telescope key project. This was not a pre-allocated block of time on Hubble. This was just sort of convincing the time allocation committee year by year for coming on 20 years or 20 proposals that this was a good thing to do. And it's now totaled about 1,000 orbits, which is a fair chunk of time, probably the biggest single project in the history of the Hubble Space Telescope. Don't quote me, but I think that it's within the few. It might be the most. Okay, so what is a distance ladder? Let me just remind you, this really doesn't involve physics. This is directly empirical. You can calibrate things that live in the same locations or hosts as other things. So for example, in the anchor step, we can calibrate Cepheid variables either in the Milky Way or nearby galaxies geometrically, maybe with parallax, or I'll talk about other ways. Then in step 2, once you've calibrated the Cepheids, if you can find Cepheid variables in the hosts of galaxies that recently had a type 1a supernova that are in range, that's about 10 to 40 megaparsecs, you can calibrate those. And then type 1a supernovae are seen all the way out to redshift of 1 or 2. And so they well measure the expansion rate of the universe. So as I said, this route does not involve astrophysical modeling. Just a misconception I want to clear up is we don't use stellar modeling or stellar evolution. This is empirical. It's based on the idea that there's nothing different about Cepheid variables because they're on rung 1 versus being on rung 2. And there's nothing different about type 1a supernovae because they're on rung 2 versus being on rung 3. And all of these measures are in the very nearby universe where there is very little chance for evolution because the look back time is very small. However, it is still critical to make the measurements as similarly as possible for the same kinds of objects across rungs. And I'm going to describe, we put a lot of effort really into that particular step, and I'll say more about that in a bit. Okay, so parallaxes have improved dramatically in the last decade. This is really probably the area of greatest improvement in the entire work on recent Hubble constant measurements. The reason this used to be hard was that stars, particularly Cepheid variables, which are not the most common stars, tend to be pretty far away, kiloparsecs away, which means that their parallax angle, the angle through which a star moves as it goes around the Earth, is less than a milliarc second. And you want to measure that well. So just to put this in context, we're looking to be able to measure that, let's say, a Cepheid variable wanders back and forth every 6 months by 1/100th of a pixel on the Hubble Space Telescope's main camera. And so we need to be able to measure to greater precision than that. So back about 10 years ago, when we were desperate to make these kinds of measurements, this was before Gaia launched and Hipparcos couldn't make measurements this precise, we came up with a way to improve the precision of astrometry measurements to reach the parallaxes we wanted to reach. And that was by spatially scanning the telescope, the Hubble Space Telescope, so that instead of observing points of light, we observed lines of light, and then we could beat down our errors by comparing the separation between stars averaged over thousands of pixels. This technique could reach 20 to 40 micro-arcseconds. It does reach, in fact, that precision. It's just painstaking because you have to observe and campaign on object by object. But we persevered with this up until around 2018 and measured for 8 Milky Way Cepheids, long period Cepheids, their parallaxes. So what you see, each little graph here is one Milky Way Cepheid, and the back and forth motion, the amplitude is the parallax. So the inverse is the distance. This was good enough to reach a 3% calibration done fully on the Hubble Space Telescope system. So that means not just the astrometry from Hubble, but also the fluxes or the photometry of the Cepheids, which is crucial because we're going to compare these Cepheids to the ones in supernova hosts. So that was about the best you can do until Gaia, particularly data release 2 and then data release 3, provided even better parallaxes over the entire sky. So we targeted 75 Milky Way Cepheids, the longest period ones, and just measured their fluxes with HST. So therefore, we can combine the best of both worlds, the fluxes from HST, which we need to be able to compare to distant Cepheids, but the astrometry, the parallax is coming from Gaia. And so this is what I would call approach 2. And I'm going to tell you also a little bit about what I would call approach 2.5, which is sort of even a little bit better. You might wonder, how could you get better parallaxes than the ones that Gaia produces now for individual Cepheids? And the answer is some Cepheids, about 20 or so, live in clusters of stars, hundreds to thousands of stars in open clusters. And so in those cases, you can average hundreds or thousands of stars to get the parallax to higher precision than the individual Cepheid. And with this technique, we can get down to 10 micro arcseconds. And both approach 2, the direct parallaxes of Cepheids, or approach 2.5, the parallaxes of the clusters that the Cepheids live in, get you to about 1%. And we published this latter result just a couple of months ago. So if we look at sort of where this gets us, in the year 2022, we now have 3 different, and I would say relatively independent in terms of systematics, ways to measure parallaxes of Milky Way Cepheids. The spatial scanning from Hubble, the individual Cepheids in green there, and the cluster Cepheids. And you notice the cluster Cepheids in red. There are certainly not as many of them, but they have the highest precision of all. You see their scatter is even smaller. We are still in the process of collecting more of these in cycle 30 with the Hubble Space Telescope. And after we do this, and particularly when Gaia reaches its final advertised precision, that means in data release 4 and data release 5, this step alone should get to 0.4% uncertainty in the Hubble constant. And so this will really be, I think, the cornerstone of local distance measurements. Now, parallaxes are not the only way to geometrically calibrate Cepheid variables. You can also observe Cepheid variables in our nearest neighbor, the Large Magellanic Cloud, which also hosts dozens of detached eclipsing binary systems, which can be measured, their distances can be measured geometrically by timing the eclipses as the binary system orbits, and you can measure interferometry of red giant stars to determine the geometric distance through a relation between the surface brightness of these stars and the physical size. And so that is a powerful method. And the third method, also independent of the other two, is water masers in the galaxy NGC 4258, which has a supermassive black hole in the center, And by observing the proper motion of these water masers over decades and their acceleration, you can measure their Keplerian motion and measure a geometric distance. So these three techniques currently are good to 1%, 1.3%, and 1.5%. Most importantly is they're independent in terms of uncertainties, and you can measure the Cepheid variables in each of these three locations with Hubble to make sure they're on the same 0 point as distant ones. Step two is to observe Cepheid variables in nearby galaxies that recently hosted a Type 1a supernova. This is really the rate limiting step for measuring the Hubble constant, because there are not so many galaxies within range of Cepheid variables that hosted a Type 1a supernova. There's about one per year or so. And so if you collect all the well-observed Type 1a supernovae that have been observed in the last 40 years, and you can't go earlier than that, or you're not in the era of digital photometry, there are about 40 such Type 1a supernovae. We have been persistently, I would say, collecting these over the last 15 to 20 years. And this last data release earlier this year more than doubled the sample from 19 to 42 and completed the sample as well. These are all the ones up through the year 2021 that were in range. So this is a sample that's not going to be doubled again, not in the lifetime of Hubble at least. So we have to make the most of it as we can. Wenlong Wan, who is a postdoc working with me, wrote a great Cepheid finding pipeline that we use heavily for this work. Okay, so these were the first 19 hosts that we published in 2016, and these are the 23 new Type 1a supernova hosts. We also observed more fields in NGC 4258 to improve the calibration and the tie to that location. How do we find Cepheid variables? It's actually pretty straightforward once you have good photometry. They vary, as you see. They have characteristic light curves that look sort of sawtoothed, and you also use the light curves, obviously, to measure their periods as well. And then for each of the galaxies, you define period luminosity relations that constrain the distance to each of the galaxies as well as the anchors. As I said, the key element here, why we can really do better than, if you're thinking, well, why didn't Sandage and DeVoe-Colors do better, is because we have the Hubble Space Telescope, and we can use it now to observe Cepheid variables in faraway galaxies, but also in the nearby anchors on the same photometric system. And so everything has been done in this matched way. And we also have a near-infrared camera that was not available in prior years that allows us to observe Cepheid variables in the near-infrared where they are better distance indicators. This is on the right, the period luminosity relations in the Large Magellanic Cloud. And as you go from optical at the bottom to near-infrared to de-reddened near-infrared, you get down to dispersions of just 3% in distance. So they become very good indicators, and that's great. Okay, step three is to measure the Hubble flow with Type 1a supernovae. This is a Hubble diagram. This is produced from the latest supernova compilation, Pantheon Plus, which is produced by Dylan Brout and Dan Skolnick. We measure the intercept of this Hubble diagram. We avoid doing this too nearby, so we're not sensitive to flows, and we don't go to too high a redshift, so we don't have to take too much accounting, at least, for changes in the expansion rate. So there's this sort of sweet spot you see there. And we now model the covariance between supernovae as well. All of this data is public, and you can find all of this data, both the supernova data and the Cepheid data, on this GitHub site, just linked there. It's also listed in the papers. If there's anything else you need, let us know, but this is all the data needed to reproduce these results starting from the raw photometry. Okay, so you combine these three steps that I talked about, and that produces this sort of continuous distance ladder that you see here with the multiple independent geometric calibrators, the middle panel where Cepheids calibrate Type 1a supernovae, and then Type 1a supernovae out into the Hubble flow. And then, as I said, we for the first time modeled the covariance both between supernovae and Cepheids. That's where we now include systematic uncertainties. I can talk more about that if people have questions. And then after that, it's a simultaneous fit with 5 free parameters that are global. Oops, I didn't list those. The five free parameters are two fiducial luminosities, one of type 1a supernovae, one of Cepheid variables, two parameters that describe the relation between Cepheids and luminosity. One is the slope with period, and the other is the slope with metallicity. And the last term is 5 log H naught, which of course is the parameter most people are interested in. So when we do these fits, we now get 73.04 plus or minus 1.04. This is symmetric in 5 log H naught, but it's not symmetric in H naught, so you have to account for that. We get a good chi-square per degree of freedom for 3,500 data points, and this is formally 5 sigma from the Planck values. If you look at the chains that we run, we include the Planck chains here as well. We run out to 100 million samples to sample the 5 sigma tails, and you can see we really are 5 sigma from that. So that's the result. Now let's move on to scrutinize it. So first question, which people have had from time to time, is how consistent are these 3 different anchors? And in this current iteration, they're very consistent. The best way to show that is to use 2 anchors to predict the third. That is, you use the geometric distances to the 2 anchors, and you don't use the third one, but you use the Cepheids in the third one to predict what its distance ought to be. And so what I'm showing you is that in blue is what the geometric distance is to 4258 or the Milky Way or the LMC, and in green are samples from the chains, not including that third anchor. You can see they're consistent within a sigma, and the different values you get for the Hubble constant, 72.5, 73, 73.5, and just as I said before, these have independent systematics in terms of the geometric distance. Okay, how about the photometry? We put a lot of effort into the photometry in this round. We have 2 independent tests of the absolute photometry. One is, instead of using PSF photometry, we use aperture photometry. And the other is, there's another group, the Araucaria project, which has gone back to the original pixels in the HST archive and has measured the Cepheid variables in the richest Cepheid galaxy, NGC 5584, and got very similar results, I think, to 1%. We also provide 6 validation tests of the backgrounds or crowding. What do I mean by that? Well, Cepheid variables live in galaxies, and there are other stars superimposed on them, and you have to account for what is the mean background. Now, if the Cepheids live in an outer region, like in blue, these blue boxes you see, then the fields are very sparse, and so very little accounting is needed. You can just see and measure the Cepheid variable independent of anything else. If they're in denser regions, like it says here, this inner region, then you measure the Cepheid variable, but then you have to throw down what we call fake or artificial stars in the frame and measure those as well to account for any bias or really to accurately measure the background. Now, what's nice, and it provides a strong test, is you have some galaxies where you have both, ones in dense regions and ones in empty regions. And since this galaxy has to have one distance from us, you can use the requirement to test the precision of your distances. So that's shown here for the period luminosity relation for each type, and they agree to about 100th of a magnitude, certainly well within the errors that we provide here. And so we see no evidence of any kind of bias in our measurements. Other tests that we do, we look at the residuals of the global fit as a function of the local background, because the local background is not part of the distance ladder measurement. And so if we were over or underestimating the background, you would see residuals which are not consistent with 0. And in fact, there's a particular pattern you're looking for to solve the Hubble tension, and that would be to either underestimate, let me get this right, underestimate the background in Cepheid and supernova hosts so that the red points would follow the red line, or overestimate the background in the anchor Cepheids in NGC 4258, for instance, that the points should follow the black dashed curve, the black points. And neither of those are true. The data passes this null test. And something else we've looked at is simply the value of the Hubble constant as you go from the including all Cepheids, that's over here on the right, to eliminating Cepheids in the densest regions of galaxies. And you can really take this pretty extreme. We go down to about, we only have a quarter of the whole sample of Cepheids left, and we see no action or real change in the value of the Hubble constant. Also, we can divide just the set of hosts into the ones that are the most crowded and least crowded, and that has very little effect on the value of the Hubble constant. Of course, the best way ultimately to get sparser region of Cepheids is to use a telescope with higher resolution. It does that optically or naturally simply by resolving everything better. And so JWST will give us measurements making all Cepheids look like the least crowded, third or 40% or so. And as shown here, that doesn't seem to change the value of the Hubble constant. However, we got a serendipitous observation. There are a couple of programs, ours and from the CCHP group, that will be observing Cepheid variables, tip of the red giant branch, and other indicators with JWST. Most of those observations are still in the future. However, there was a serendipitous observation of one galaxy, NGC 1365, which is one of the ones in our sample, hosted a type 1a supernova, and we knew where the Cepheid variables were. They had been observed with HST, shown here in these squares, red and green and blue squares here. And then with NearCam on JWST, observation here, this purple rectangle, and you can see a little area of overlap here just by chance, observed a handful of Cepheid variables. And when you look at these, it's really impressive what the new telescope can do. Going from the optical HST to the near infrared, and that's the goal here, is to be able to observe Cepheids in near infrared. I'll just show you two Cepheids, this one here in orange and this one in blue, comparing HST in the near infrared to JWST in the near infrared. And if you just look and see how much more detail, you see how much better resolution, it's really quite remarkable. And so we really look forward to using JWST for these kinds of measurements. However, just for this first case, we were able to test the accuracy of the distance measurement for compete between HST and JWST. And so using the initial calibration of JWST, the points in red are from JWST and in gray are from HST. Now, I just want to emphasize this observation was not optimal for JWST. It was not the depth we would like. It was not the location we would like. It was a random phase. It wasn't multiple phases to reduce uncertainties due to just the periodicity of the light curve. It wasn't the wavelength I would choose. The calibration is preliminary. So given all those caveats, there is good preliminary agreement, strong enough to say we see no evidence of would have to be a 0.2 of a magnitude shift to resolve or solve the Hubble tension. But the best is really yet to come with these cycle 1 programs. We'll have more observations like this. So I certainly look forward to this, but I would say no surprises so far. Other questions people ask: could we live in a giant void that is causing our local Hubble constant to look larger? I would say the answer here is no. Both large-scale structure theory and the supernova Hubble diagram itself really rule this out or limit it to about 0.6% in the Hubble constant. Is Hubble linear enough to make these measurements? Yes, this is something I work on in my work at Space Telescope Science Institute. It's been calibrated now across 15 magnitudes to be good to about 0.3%. Do the Cepheid backgrounds compromise their accuracy? I've talked about some tests. We also can look at the amplitudes of the Cepheid light curves. And if we were missing background, it would compress the amplitudes because you're combining a constant thing with a variable thing, and we don't see evidence for that. Is there a difference in the supernovae at the two ends of the distance ladder? We've taken a close look at this by looking at the residuals of the Hubble diagram with everything we could think of. There's a good paper by Jones et al. Any correlations are less than 2 sigma and would limit the contribution to an error in H naught to about 0.3%. Are the different anchors consistent? I discussed that already. This is largely responsible due to the abundance dependence of Cepheid variables, which is about 0.2 of a magnitude per dex. And I direct you to a paper by Luisa Bruval and Pierre Carvala on this that just came out this year that I think explains this in much greater detail. Are TRGB and Cepheid distances consistent? They are when you start at the same anchor and you go to the same supernova host. This is covered in a couple of papers, and I can discuss this in more detail. We also include TRGB measurements in our results and get 72.5 instead of 73 when we do that formally. Can you resolve the tension by changing the dust law in each host? The answer here is no. However, in the last year or so, people have made some errors in some papers by not first separating the intrinsic color of Cepheids from the extrinsic color, the part that dust can affect. But when you do that, there's no really way to make any movement here because we're making our observations in the near infrared. We go through 67 variants of our analysis in the paper. Here are some of the, I would say, greatest hits ones of different ideas people have had. You can move the Hubble constant around a little bit, but the bottom line here is it's very difficult to get below 72.5 or above about 73.5, but we do propagate additional uncertainty of the dispersion of these variants as an extra systematic uncertainty. Okay, so just to be clear, this is a long-standing problem. This is not something that just popped up. I would say for the last 20 years, we have systematically seen that observations of Cepheids and type 1a supernovae have been giving this higher Hubble constant. It's just that the uncertainties have come down enough that we are starting to say, hey, this is really significant. When different people do the analysis or different groups measure different Cepheids using different instruments, they get the same thing more or less. And so this is really something to contend with. And as I advertised, there's been a group now that really went back to first principles here, the original pixels, and used different methods and got very consistent results. This is from Javan Marty et al. In the FJ. Okay, so if you haven't been paying attention until now, I would say it's a good time to pay attention to it, that we've gone past the point of just wishing and waiting for this to go away or thinking it was just statistics or systematics that people could kind of put into words that we could actually test. I think another way to describe this tension is just a note that there's really no precise local measurements of the Hubble constant that are coming in lower than Planck. And so that is why we're so intrigued by this. There's been many conferences and reviews which have pointed out that techniques, there really doesn't seem to be, the result doesn't seem to depend on the use of any particular method, team, or source. I show here some of the most precise reference distance ladder results they're all consistent with each other, but as a whole, or using the most precise ones, they're just not consistent with what we see locally, at the early universe. And of course, to emphasize that the Planck results themselves are internally consistent with measurements that come from the early universe. Other CMB experiments, Big Bang nucleosynthesis. So that's why this is often described as an early versus late, or indirect versus direct, or tension, or a tension that depends on the accuracy of vanilla lambda CDM. Another tension to pay attention to is the sigma 8 tension, the RMS of matter fluctuations on 8 megaparsec scales also has this curiosity that when you compare the early universe measurements and use lambda CDM to predict the present value of sigma 8, you get differences with what we measure locally. This is at the 3 sigma level, but independently seen in lensing, galaxy clustering, and peculiar velocities independently. And so if you combine those, you're more like at the 4+ sigma level. And so I like to say you get extra credit if you could think of a way to solve both of these tensions with the same idea. That isn't required. You could still get an A in the course if you solve either of them, but it would be great to solve both. So what is causing this? And I don't know, and the community has lots of ideas. The most likely, the sort of, or least unlikely, seems to be ideas that affect the cosmological model at early times before recombination, particularly for the Hubble tension. If you can increase expansion before recombination, either by injecting energy or changing the sound speed or increasing inhomogeneity at early times, that can reduce the sound horizon, which is the fundamental calibration of the CMB, and also of baryon acoustic oscillations. And so lots of mechanisms have been suggested. Early dark energy, an episode of dark energy around the time of recombination, some kind of sterile neutrino with special interactions that cause it not to produce signatures in the cosmic microwave background, evolving scalar electron mass, primordial magnetic fields. There are lots of ideas. Some can get partway there, some can get all the way there, some make the fits worse. In fact, you have to go to an event like the H-Naught Olympics or the H-Naught World Cup, I should say, and to rank these different methods, these different ideas. And I'll just direct you to a few recent reviews. Some things do better, as I said, some things do worse. And I think this is a very interesting area of investigation. And many of these ideas make predictions of additional features you should see in, for example, the cosmic microwave background. And there's been some claims of maybe seeing tentative evidence for those features. There was a couple papers last year claiming some evidence in the ACT data, which wasn't necessarily consistent with Planck, but seemed to show evidence for some of these early dark energy features in the CMB. I think the jury is very much out, but the good news is, at least I hear, that ACT should have a major data release in the next year that will have much better statistics. But I think it's worth people thinking about when they're designing CMB experiments of the future, that the CMB, to my mind, still remains very interesting because there is the potential to constrain these sort of physics beyond recombination ideas. So I'll just reach a summary here. I guess this is my own personal take on this, is the present tension is very interesting unless you have a very, very strong prior on vanilla lambda CDM being just the way it is. It's easy to say it's new physics, but the data is very constraining, which is why you have to have a more detailed explanation that works. It's easy to say it's systematics. However, the measurements have gotten very mature. It's been more than 10 years. You have many independent rungs, duplicated measurements. And so you really need to put enough specificity into an idea of systematics to see if it's actually possible or if it's already ruled out by the data or by, I would say, almost the Copernican principle. I think all the known or posited systematics have been addressed to this point, but we look forward to people putting into enough specificity ideas of what else could cause this. Just saying unknown isn't really helpful or useful, I think, at this point without enough specificity, because it's very likely most of the ideas of systematics are ruled out by the null tests. However, I think there's a lot of room for optimism here. We always have to remember at the end of the day, or from the beginning of my talk, that lambda CDM is really not a fundamental theory. 95% of the universe is dark. This is a phenomenological theory, or it's really a fitting formula at some level. And of course, we lack quantum gravity. And so it's not crazy to think that there is physics beyond lambda CDM. I'd be surprised if there wasn't, and that could play a role in these tensions that we see. So I think this is very fertile ground for learning something new. Where I see our measurements going in the next few years, we now have all error terms below 1%. We have new Gaia data releases on the horizon, JWST observations on the horizon. We look forward to LIGO observations, which can play a role in this. One of the more interesting measurements I've heard about recently is using the EHT, the Event Horizon Telescope, to reobserve the masers in nearby galaxies that can get a 1 or 2% measurement of the Hubble constant, independent of everything else. The use of new facilities like DESI, Roman, Rubin, Euclid to better characterize W of Z, new CMB experiments, which can look for signatures of new physics pre-recombination. I think all of these are actually quite interesting. So my final summary, the discrepancy is around 5 sigma. There's no real precise late universe measurement that's coming in lower than any of the early ones. That makes it very intriguing. It appears robust because it would require multiple, I'm going to say, catastrophic failures of measurements that seem independent to avoid this conclusion. So unless you're very strongly wedded to vanilla lambda CDM, this is certainly worth paying attention to. And to remind ourselves, we're not dealing with Maxwell's equations in cosmology. These are still phenomenological models, and we have to continue to seek explanations that make testable predictions. So I will end there, and I'm happy to take any questions that you have.
Thanks very much, Adam, for this great talk. Thanks a lot. We have really, and we have time for questions, points. So please, participants, raise your hands and then we will proceed, and then you will be able to address your questions and comments to Adam. So please. I only see congratulations to you, Adam, not yet questions. So perhaps I can open and always, here we have one question by Scott Walter, please activate your microphone. And proceed to your question, please. I don't hear.
Go ahead, Scott.
Yes, please.
So I see your lips moving, but I don't hear anything yet. Are you muted?
No, it's not muted.
Do you hear him? I'm not hearing.
Yes, yeah. We don't hear you, Scott.
I can hear Scott.
Oh, you can?
Yes, loud and clear.
Now we hear. Oh. Now we hear you. No. It's your system.
Maybe you could put the question in the chat, or
yes.
If somebody else hears it and can relay it.
Yes, and so meanwhile, we can proceed if there are other questions or comments. No other questions. So the question by Scott Walter.
Oh, okay. So Scott's question was, elaborate please on the characterization of distance ladder as empirical. Okay. So what I mean is, and I guess I could go back to maybe that I could find that slide. What I mean is that it is just a system of linear equations here. Right, so there's no theory involved. There's no modeling of Cepheids or type 1a supernovae. The only assumption is that, once these objects are standardized, which they're done locally, that there's no difference in the luminosity between a supernova or a Cepheid just because it's located on the first rung versus the second rung. Or, another way to say that is, that there wouldn't be a difference for Cepheids just because they're within 10 megaparsecs than being within 40 megaparsecs. Or for supernovae, that they're within, redshift of 0.01 versus 0.1. And those are all small look back times. And so that's what I mean by it's empirical then.
Other questions, comments? Well.
Yes, I have a question, Adam.
Thierry Midavine.
Are you able to hear me?
Yes.
May we have a bias when we are looking at very far distance, deep in the universe, due to the fact that all the galaxies we detect, where we are able to detect either Cepheid or, of course, supernovae, is amplified by a gravitational lens.
Right. So gravitational lensing of supernovae has an effect sort of in one of two ways. Either there can be strong lensing if you have a lot of clustering along the line of sight, or there could be a more weaker sort of weak lensing de-amplification because most lines of sight are empty relative to strong lines of sight. Those effects, particularly the de-lensing effect, doesn't really become significant until you look through a very long distance, usually beyond about a redshift of 1. And so everything we're doing is on much smaller scales than that. So short of looking at, a type 1a supernova with clustering, along the line of sight, and in all cases, that's not the case here because, again, these are very local. There are no supermassive clusters on scales of redshift 0.05. And so it just doesn't really play any role. It's more relevant in the high redshift universe.
Okay, thank you.
Sure. Let's see, here's a question. The CMB is emitted during a process where the primordial plasma is undergoing a change in equilibrium that necessarily takes some time. How likely is it that early H0 could be influenced by this fact? Undergoing a change in equilibrium. I'm not sure if I'm getting this question right. I mean, the CMB is very well, the early time plasma is very well mixed, other than coming through, recombination. I think we generally assume that the plasma is very homogeneous. So unless there are, some ideas have been posited, have been things like strong magnetic fields that produce inhomogeneities. And I mean, those are ideas that could affect things. But right now, there's no really good model other than to just say that in words.
Thank you, Adam and Bill. Other questions, comment? If not, I have Raf Hoffman,
yes.
please.
Yes.
Please.
Adam, is there a consensus why the tip of the red giant branch distance calibrations yield lower values of the Hubble parameter than supernovae? What's the status on that right now?
Yeah. So the tip of the red giant branch involves measuring the distance to a galaxy by looking for this break between the red giant branch and AGB stars. And so that break is often quite fuzzy. I think generally it's not as easy to measure as Cepheid variables have. So here's the same galaxy where you're measuring this feature, the tip of the red giant branch, and trying to locate it versus here the Cepheid light curves. Now, to answer your question, I would say that there's been a broad range of H0 measurements coming from tip of the red giant branch. Here are several of the most recent ones in the last few years, and this range is sort of 70 to 76, depending on whether you use tip of the red giant branch to calibrate surface brightness fluctuations, type 1a supernovae, or Tully-Fisher. And the lowest measurement that I've seen is one from the CCHP group, which comes in at 70. So is formally consistent with either the Planck value or the value you get from other distance indicators. And why is that? Well, it really comes down largely to the calibration of tip of the red giant branch. So because tip of the red giant branch is not a type of star, it's actually a feature in the luminosity function of thousands of stars. You can't just directly measure the parallax of tip of the red giant branch the way you can for, let's say, Cepheid variables or other distance indicators. It's trickier. And so as a result, there has been a broader range of uncertainty in the calibration. So what I'm showing you here are calibrations collected over the last 5 years or so. And so I'm showing you here the range in luminosity, and that range in luminosity explains a lot of the range in values people get for H0 when they employ tip of the red giant branch. So the most luminous gives you the lowest, and less luminous gives you higher. If you look at values that are coming from Gaia doing statistical analyses, or by measuring the distance to Omega Centauri, which is a compact globular cluster where you can measure tip of the red giant branch, you tend to get values around 72 or 73. Also, there's a recent paper by collaborators of mine that is, I think, worth paying attention to, showing that tip of the red giant branch itself is not a perfect standard candle, that there is a dependence or variability in the luminosity of the tip of the red giant branch that probably depends on the star formation history or metallicity of the galaxy, but that can be tracked empirically through the contrast ratio, basically how fuzzy that tip is. And I think that when it's fully analyzed will help explain some of this range of luminosity of TRGB. So I would say stay tuned for that.
All right, thank you very much.
Thank you. More questions? Well, I have quick questions or points. First, you clearly show preliminary chain wave agreement set with HHT for your measurements, in which from here for the future, how much time do you think do you need to have some, I mean, more definitive, even if the trend is very clear? I mean, I am convinced, as you know, but it would be interesting to know how much take this program with James Webb.
Yeah. So most of the observations from James Webb that are going to be taken that are relevant to this will be taken in the first half of 2023. And so, you know, I would imagine, you know, 6 months to a year after that we should have results from multiple groups.
So for next lecture here, you will be
hopefully
maybe said that. And the other point is that it's appear very clear, I mean, for your complete work and collaborators, that the problem is the two, is the two scales, the late anchors, I mean, all what you show, whatever the measurements you do, you again strongly and robustly confirms and ameliorates the precision. And on the other hand is the early scale, I mean, and all CMB, I mean, it's not a problem of Planck, perhaps, or of CMB. It's just the fact that what is analyzed of the early data for said before recombination and the sound horizon scale, it seems does not take into account all the physics of the early universe, which, by the way, is not completely known as the late universe. So there perhaps too is a problem of calibration for the CMB, another way to calibrate. I mean, I don't know, but it seems to me, because I mean, elaborating on what we had here, different lectures on neutrinos and quantum, I mean, the and dark energy. It seems to me that the likely solution set or proposal, the good ones, are early dark energy, primordial magnetic fields, because anyway, I mean, are not so exotic and neutrinos, which are asked, yes, which are asked also from the particle physics sector.
Right.
But is still, I finish very quickly, and I leave you, Adam, please. And it seems that taking separately the way in which this has been proposed till now, because it must be worked more, have not are in the good direction, but do not are not enough for the 5 sigma needed for the discrepancy or the problem of the H0. Perhaps combining that or implementing early dark energy in a different way, which is what I think too. But in any case, primordial magnetic fields and neutrinos are doing in the right direction. So now, please, Adam.
Well, I would say the ideas people have proposed are enough to convince that there are possibilities, that there is some wiggle room with the right model or physics. I mean, I would say the CMB is an excellent fit to vanilla lambda CDM, but that doesn't mean that there isn't additional physics that at the moment the CMB is not revealing internally, and that some of these ideas can demonstrate, oh, you could even improve the fit to the CMB a little bit with some of these. But these may be just placeholder ideas for, what is the real thing that's going on. I mean, I think they're very useful placeholders because, they may be pointing to directions. Like we may see, a better idea that has elements of these or acts at the same period or acts with a similar mechanism, but it does it in some different way. So, I don't know the answer. I'm not satisfied that we have the full set of ideas and we have to pick between amongst one of these. But I think it's, we have a lot of problems in cosmology. I mean, lambda CDM, lambda itself is a big problem. People often say to me, well, I mean, it would be so strange if something else was going on. I mean, we have lambda CDM. And, I often point out, I mean, lambda is just an idea, in any kind of quantitative, specific, discrete way, we don't have an explanation for it. So, you have to keep in mind that we've been happy in the past to come up with names for things and just a general kind of fudge factor for it and move on. But that doesn't mean that we finished or satisfied any detailed explanation there. And so if then cracks show up when we use that description, I don't think we should be that surprised. So I just think, we have more work to do, both on theory and observation.
I totally agree, and please allow me to go in this direction. The CDM is a phenomenological framework.
Yeah, it's powerful. It's very powerful. It's just, it's just not complete. Yeah. It's not complete. It's hoping that the simplest phenomenological, the simplest number of parameters, or however you want to describe it, is ultimately everything, and that we'll have a theory that says, oh yeah, it had to be the simplest one. But we don't know that really now. So, we have to be open to ideas beyond that, especially when we start to see, strong empirical evidence of tensions.
Yes. One other tension, but I will not associate to this. It's not correlated, but it's another tension, is sigma 8, ACE 8 for the clustering. I think that is more connected with dark matter. With
well, I don't know. Yeah.
With the dark matter part of lambda CDM set, which is not so cold set, because in the way we know, I mean, in the standard way, is not cold but frozen. Is too much cold. But anyway, the other point I want to make, because you mentioned, and it's very good, I mean, because there are other discrepancies for lambda. For instance, you said the mismatch between the particle physics vacuum evaluated, which is 10 power 122, and the observed value today, which is much more. I mean, it's a huge discrepancy. However, I think, and that can be elaborated, I mean, there are recent work on that these two values the very high evaluation from particle physics and the observed one today refers to the same physical quantity, vacuum energy, but in two different states of the universe. Once the very high value is that associated to the very, very early and quantum. In fact, the value is really quantum gravity, the high value of lambda, and that is associated to a state of the universe, a quantum state, which is very early. While the value you observed, and the value of lambda today, the very low, is correct too, but that corresponds to a classical non-quantum state of the universe, which is very, very diluted, is very void. In fact, one observes, as astronomers do not call vacuum, but call voids. And this, I think, in these two different states, one quantum very early associated to the high value of lambda, and the other very classical from the point of view of gravity, very dilute, are the voids,
sure,
and very low, are correct in their own states and can be associated from what is called, the wave particle or the classical quantum duality for gravity. So this is another point also which is good to understand, and which supports the vacuum, the cosmological vacuum energy of the universe, which is associated to H0, to lambda, and to your discovery of the acceleration. Because in fact, Adam, expansion accelerated is also in the early universe, because there are inflation and driven by the vacuum energy, which is quantum, not semi-classical set, semi-quantum.
If I could break,
yes.
If I could break in for 1 minute, I have to go catch a flight, but thank you very much for hosting me.
So I would like to make a toast for you and for all Kelt and participants with True French Champagne, as you know, and all good wishes, and thank you, and keep time it, as you said, because more, I wish all success with this H0 value to really.
Thank you.
To really.
Thank you. I hope everybody there has a great new year.
Yes. Thank you, Adam. Bye-bye.
Thank you.
Take care.
Get well. Have a good flight. Bye-bye.
Good flight.